Welcome back everyone to section 3.2 of my mini course on Semiclassics. Now I would like to explain to you how to adapt the ideas we introduced in a previous section on how to make Semiclassics rigorous and adapt them to systems with an underlying periodic structure. So the types of systems that we initially dealt with is on the left. So for the sake of concreteness, let me also remind you of what the Hamiltonian was. So this was H epsilon is equal to minus Laplace plus V of Q epsilon, where Q epsilon is just epsilon times the position operator. So here the potential is assumed to be regular enough. So we've explored this point a little bit in the previous section. And now let's compare and contrast this to the situation in condensed matter. So here the Hamiltonian is slightly different. Let me say that for simplicity, I'm assuming that in both systems, there are no magnetic fields. So both the magnetic field is zero and the vector potential. So what I have is minus Laplace plus the periodic potential plus the slowly varying external potential. And let me rename this, the first part. So let me put brackets around the first two. This is just H periodic plus V of epsilon. Of phi of epsilon x hat. So here the periodic potential in red need not be regular. So this is indicated in the picture. So here, you just have a periodic square wave. Of course, this is just a one-dimensional sketch, but the point is that here we need not make any assumptions on the regularity, because what matters to us is the regularity of the energy bands and the regularity of the Bloch waves, the associated eigenfunctions. So it's not about the potential, it is about both terms taken together. And since the local analyticity comes from the Laplacian, we need not make any regularity assumptions on the periodic potential. To make it a little bit easier to make the comparison, let me just replace the V on the left by phi. So I'm not doing anything here, I'm just relabeling. So also here, this will become a phi. And an important point is that this is another commonality, is that both systems have a small a two-scale structure. So on the ordinary side, the microscopic scale is given by a chosen wave function, and the macroscopic scale is determined by the scale on which the external potential varies. and this is given in terms of the small parameter epsilon, which is just the ratio of microscopic to macroscopic length scale. On the condensed matter side, on the other hand, the situation is similar on the one hand, but slightly different on the other. So here, the small structure is fixed by the periodic potential. So the small spatial scale is given by the periodic potential, and the large scale is given by the scale on which the external potential, here just the electrostatic potential phi, varies. So in both cases also we are interested in states whose energy is order 1. So so let me write this down. So we have the semi-classical parameter epsilon. That is the ratio of microscopic to macroscopic length scale. The second thing is that states we are interested in of order 1. That means the energy as you scale epsilon, so as you scale epsilon to 0, the energy remains fixed. Well, it doesn't have to remain fixed, but it should neither explode nor go to 0. So it should be the point is it should remain order 1. So what does that mean? Well, here we are on the in both cases we are using microscopic spatial units. So that means we're keeping this here fixed. We're keeping the microscopic size fixed. And as we let epsilon go to 0, we increase the macroscopic distance. And for example, if we, since phi is supposed to be regular, let's say it is also bounded just to avoid some technical complications. So for example, if phi is bounded, then the kinetic energy will be the same. There's no epsilon dependence here, and we just keep this the size of the wave packet fixed, which means we're keeping the frequencies here fixed. And all we are changing is this here, but since the value of the potentials that we can explore with the wave packets is the same, thus the energy remains roughly the same. And the same is true here. What we do here is we're keeping the microscopic length scale fixed, and we're considering Bloch waves. Instead, here we're considering plane waves, because these are the eigenfunctions or pseudo-eigenfunctions to the Laplacian. And here we're using Bloch waves, which are eigenfunctions to the periodic operator. And simply by picking an energy band, we are picking also an energy. So also here, the energy remains roughly the same. And for sure, it does not explode, nor does it scale to 0. This is just important. And note that even if we were to use macroscopic units where we push the epsilon in front of the Laplacian, we would get an epsilon squared here. Nothing would change up to a rescaling. So here we would keep this here fixed, and we would scale the microscopic length scale. But even though we're shrinking the size of the wave packet here, we are compensating for that with a prefactor epsilon squared. So still the macroscopic energy remains of order 1 in both cases. Another similarity is indicated in a picture, namely that the potential, so on the left it is just the potential, on the right it is the external potential. So this needs to be sufficiently regular. So one important point in all of this is that this is also something I've just said before, is that in essence, if you want to adapt the semi-classical techniques to condensed matter systems, what you have to do is you have to replace plane waves by Bloch waves. So let me explain this point in a little bit more detail. So let me remind you of the Bloch wave picture here, and on the left, let me just copy and paste this here. So the important point is that on the left we have the quote-unquote ordinary situation, and on the right we are having the periodic situation. And let's think about the ordinary situation first, and then see how this contrasts and compares. So one key point is the connection between the Hamilton operator and the classical Hamilton function. So let's take the Hamilton operator here and take the expectation value with respect to the wave packet psi. Since energy is conserved, or rather in this case we should think of it as total probability, we need not evolve in time. And just pictorially speaking, let's zoom in a little bit. So this wave packet has an approximate mean position, which, let's say, pictorially speaking, if I integrate by I, is roughly here. And since the potential is very regular and does not change appreciably over the width of the wave packet, of course, the fidelity of this approximation is improved as we decrease epsilon. And I can already see that the kinetic, the potential energy term can be replaced by the value of the potential at the mean position of the wave packet. So this q epsilon psi, just as a reminder, this was just the expectation value of the wave function psi of the wave packet with respect to epsilon x hat. So the epsilon is included in here. And wave packets are also supposed to be well localized in momentum space. So here what I can do is I can pretend that the wave packet has a similar shape in momentum space. So this is the case exactly when you have a Gaussian, because the Fourier transform of a Gaussian is a Gaussian. Of course, this is only morally correct if you're looking at more general wave packets, but still the point is that wave packets are so these kinds of wave packets are supposed to be well localized in real space and in momentum space. And so what I can do is, if the variance of the wave packet is small, and this I can do, I can assume as well. Then the first term, the kinetic energy term, will simply be the mean momentum squared. So here we are assuming that the variance of P is small. And this is nothing but the classical Hamilton function. Evaluated at the mean position and at the mean momentum. There's also something else that's very nice about this approximation, and that is that if we're looking at the quasi-Eigen functions of the Laplacian, then these are plane waves. Then if you think of them as a function of momentum, then these guys are analytic. So in particular, they're smooth. And of course, also the kinetic energy so if you plug in just a plain wave, then this replacement becomes exact. Of course, the price you pay is that plane waves are not square integrable, so they are generalized eigenfunctions rather than proper eigenfunctions. But that's, I think, clear. So the kinetic energy, which is p squared, is also analytic. And the potential energy well, this is as regular as we would want to impose to have our mathematical statements hold. So also here, this is a sufficiently regular function. Oh, I see that I switched back to V. Of course, I initially claimed I'm going to use phi here for consistency. So this is, for example, n times continuously differentiable, perhaps even smooth. Perhaps we will impose additional boundedness assumption on the derivatives and so forth. So the point is, everything is, for example, if we impose that phi is smooth, the classical energy is a smooth function. So that's very nice. So let's try to replicate that on the periodic side. So here, one of the things that I told you was true about the periodic operator, which is plays the same role, if you have a look at it, as the kinetic energy. So this appears in the same place as kinetic energy. And also here, we can do even better. We also have an analog of plane waves. Namely, we have Bloch waves. And these Bloch waves can be chosen to be locally analytic. So the only wiggle factor here is the phase. So I have a k dependent phase. K is crystal momentum. And the thing, so there are two things that can spoil global analyticity. And one of them actually doesn't matter if we assume, as we've done here, that there are no strong magnetic fields. that's a topological obstruction, which I will not talk about too much. But the other one, and this is the one that I would like to focus on, are band crossings. And similarly, the energy band functions so just a reminder, these are this is this guy, this is E1, this is E2, this is E3, and so forth. So all of these are energy band functions. These are also, so here you have no freedom to choose a phase. These are also locally analytic away from band crossings. So now we have a more general situation here, because the analog of this diagram on the for the ordinary case, this is a picture of the kinetic energy, so to speak. This would just be a parabola. So there is only a single effective kinetic energy function and a single type of eigenfunction. But here I have many candidates depending on my value of crystal momentum and energy. I can have multiple different candidates. So for example, if I'm using a plane wave with a center that's here, I can have a state that is supported by E1, E2, E3, and so forth. So there are multiple choices in how to construct states at a given value of k and a given energy. And likewise, it does not just suffice to single out an energy window, because in general, this energy window will contain states from multiple bands. So what you have to do is you have to decide on an energy band and perhaps also on a range of crystal momentum. And but there is, or there can be an issue. Namely, if you're picking a state that is very close to a band crossing, then what may happen is that even though you're starting away from the band crossing, the wave packet propagates towards the band crossing. And then it's no longer clear what exactly happens at the band crossing, at least initially. Of course, this question has been investigated by, for example, Lasser and Teufel. Caroline Lasser and co-workers have done a lot of research on this. And the answer is that there is no simple semi-classical limit, but basically you have semi-classical behavior up until the vicinity, and then you have to use some sort of energy band hopping algorithm. But this lies outside of a simple semi-classical approximation. So you have to do something more sophisticated. So it's semi-classic plus a non-classical jump. So what I will have to assume here is that the relevant states are sufficiently far away from a band crossing. But because this is a more, let's say, more difficult, that adds some complexity to the arguments, there's also another choice that I can make. And that is, I can instead choose an energy band that is isolated from the other bands, like the band E3. There's also a second thing that is relevant in condensed matter, and that is that only states that are close to the so-called Fermi energy are mobile. And the reason is that if you want this state to move, then by the Pauli principle, you would have to displace a whole bunch of other states. And eventually that means that some states have to go from this band to the next band or to some upper bands, right? So the Pauli exclusion principle says that all states, so this is the zero temperature approximation, but it still holds true for finite relevant temperatures, is that all states up until the Fermi energy are completely full, and all states above are completely empty. And if the temperature is finite, then this is still true up to an exponentially small modification of what I'm saying. So there you have to use the Fermi-Dirac distribution for finite temperature. So the point is that only states that are close to the Fermi energy are relevant. And if we assume, of course, that this Fermi energy lies close to a band crossing or is exactly at a band crossing, then we cannot expect semi-classical behavior in, well, at least in the simple setting. So we have to assume that the Fermi energy lies away from band crossings. And another simplification is, well, let's just assume that the Fermi energy intersects only a single band. This is just a simplification to make the arguments a little bit easier. Because if we do this now, let's assume that the Fermi energy just intersects only the band E3, and that the band E3 is separated from the other bands by a gap. So here this is indicated by this dashed line. As you can see, the red band E3 does not intersect with the green or the orange family of bands. So then for states, that are from the relevant subspace, and this relevant subspace well, let me just use a delta that is big enough to cover the whole range of the energy band function E3, but that is small enough so that it does not intersect with the orange or the green family of bands, with the other bands. So if I plug this in, then after Fourier transform, what do I get? So if you remember, F gamma was a variant of the discrete Fourier transform. Well, I have the kinetic part, which is just a multiplication operator in K. So remember, the kinetic part just comes from the periodic operator. And it is the band E3 by choice of my
relevant subspace. And then I have the expectation value with respect to the slowly varying potential. So, and also here you see that this is conceptually the same as this here. So the if you're going to the momentum representation minus the Laplacian becomes p squared. Here the momentum representation is given by the discrete Fourier transform. Oh, I see this is cut off. So this is given by the discrete Fourier transform, and the term that comes from the periodic operator simplifies to E3 simply because if the elements of this subspace are, after Fourier transform, spanned by Bloch waves phi 3, because I'm only choosing E3, so the only states that contribute are Bloch waves associated with the band E3, so phi 3. And so the periodic operator, since it satisfies the eigenvalue equation, so the Bloch waves satisfy the eigenvalue equation to E3, I can replace the periodic operator simply by E3. And then I have to add the expectation value of the potential. So this looks very, very similar, and this suggests that this is basically the recipe that we need to generalize. So let me close this section by saying that, okay, if we want to extract something out of this for the problem, let us add an assumption on the external fields. And that is that the electrostatic potential and the components of the magnetic field are smooth, bounded, and have bounded derivatives to any order. So this is what this means. Smooth is clear, bounded and bounded derivatives to any order. And the magnetic vector potential has components that are polynomially bounded and smooth. And of course, the exterior derivative should be equal to b. Just a small note, we cannot assume, if we want bounded magnetic fields, the simplest case would be a constant magnetic field. And one might be tempted to say, okay, I'm just choosing a bounded smooth vector potential, but that's not possible, because for a constant magnetic field that is non-zero, the vector potential at least has to grow linearly, right? I mean, it's quite clear. The exterior derivative is like a version of the derivative, and a function whose derivative is bounded has to grow linearly, and that's why you need polynomially bounded. So these are the assumptions. In the future, when I say the magnetic field and the potentials are regular enough, this is the assumption that I'm referring to. All right, and with that, let's finish this section and then talk about a rough overview of the semi-classical techniques that we have at our disposal.